let's look at a second example where now we're not trying to reduce a complicated system, but rather we're using some of our basic forms in order to help us design the system. So for this example, we want to design this feedback system. So we want to choose a value of our gain k such that our percent overshoot is 10%. And so we can see our system is relatively simple. We only have this feedback form. Again, we have the negative feedback. So what we're going to do is we can define a g sub e, some equivalent transfer function, and that's going to be equal to, we're going to have our g of s in the numerator divided by 1, and we're going to add, because again we have negative feedback, so because we have a negative here we use a plus sign here, plus our g of s times h of s. Now in this case we don't have any h of s block, so what that means is that our h of s is just going to be equal to 1, so we have unity feedback. And of course our g of s is going to be this term up here in our block, our k divided by s times s plus 5. So let's go ahead and substitute that in to get our equivalent transfer function. So we can say g sub e is equal to our g, which is k divided by s squared plus 5s, so I've gone ahead and multiplied through that s term, divided by 1 plus that same term which is in the numerator, so k divided by s squared plus 5s. And so what we can see is that would reduce to k divided by s squared plus 5s plus k. And so the easiest way to do that is just to multiply numerator and denominator by that s squared plus 5s. So for example, if we come into here and we say s squared plus 5s and s squared plus 5s, of course that's going to cancel out here and here, and we're going to be left with the s squared plus 5s times this term, and then we have the plus k in the denominator and then the single k in the numerator. So that's just sort of a good general way to deal with that if we have that unity feedback. Okay, so at this point we've got our equivalent transfer function. So what we want to do is we want to compare this then to our general form, which we talked about in our time response unit. So compare to our general form. And doing so, what we're going to focus on is this term here and our constant term. And the reason we want to do that is because we know that our 2 zeta omega n is equal to 5, so that middle term. And we also know that our omega n is equal to k. And again, we want to be careful to always use this k in the denominator, or this term here, as opposed to the numerator. In this case, we have a unity gain function, but in some cases we might not, in which case the numerator term would not be equal to our omega sub n. And sorry, I've written that incorrectly. This should be the square root of k. So rearranging, sort of combining those two, we can get that our damping ratio zeta is equal to 5 divided by 2 times the square root of k. And now the specification that we wanted to design for was our percent overshoot. And so as you recall, we can relate our percent overshoot to our damping ratio. So we had an equation, we said percent overshoot is actually only dependent on our damping ratio. So we can rearrange that equation a little bit, and we can say we know this 5 over 2 root k is equal to, and in the numerator we're going to have negative log of our desired percent overshoot, which is 10, divided by 100, and in the denominator we have the square root of pi squared plus the log squared, and again in the numerator is our desired percent overshoot of 10 divided by 100. And so if we evaluate that and solve for our k value, which appears here, what we end up getting is that our k corresponding to a 10% overshoot is approximately 17.885. And so that would be, for instance, the gain that we would set. So maybe we have a knob where we can adjust this gain value. That's what we would want to set that to in order to get a 10% overshoot. So note as well that if we want to be sort of more general, so that answers the initial statement of the problem, but if we want to be more general, what we can do is we can analyze this general transfer function here, and we can look at this denominator to get the poles of our system. So we can say, in general, the poles of our equivalent transfer function g of e of s we can get that from using our quadratic equation on the denominator. So we can say S1 of 2 is equal to, and we get -5/2 plus or minus the square root of 25 minus 4k divided by 2. And so what does this tell us exactly? So remember that our different response types have poles in different locations. So for example, overdamped, we have 2 real poles. Underdamped, we have 2 complex poles. Critically damped, we have 2 real repeated poles. And undamped, we have imaginary poles. And so what we can see is based on this k value, we're either going to have a real number or an imaginary number coming out of here. So the main takeaway there is that by adjusting k, we can actually adjust the type of response we're getting. So adjusting k leads to changes in response type. So for one value of k, we might be able to get an overdamped response. For another value, we might be able to get an underdamped response. In this case, we could also get critically damped. In this case, we can't get undamped because we're always going to have this real part, -5/2.